What we can do with data depends on the kinds of data that we collect. How can we display it, and what kinds of mathematical operations can be performed? Consider the numbers 40 and 80. The numbers 40 and 80 could describe the weights in ounces of 2 boxes. Or the numbers 40 and 80 could describe the football jersey numbers of a defensive back and tight end, respectively. Naturally, we can perform arithmetic operations on the weights of 2 boxes. 40 times 2 is 80. That is, the box that weighs 80 ounces indeed weighs twice as much as the 40-ounce box. But the same arithmetic operation, 40 times 2 equals 80, makes no sense with the jersey numbers. Those are still numerical values, but we know that mathematical operations make no sense in this case. If you take half the speed, or half the weight, of the player wearing 80, you don't get the player wearing 40. This is a straightforward example that seems like a no-brainer, but there are other examples where folks often make this mistake. There are 4 scales of measurement that generally describe data that we might collect: nominal, ordinal, interval, and ratio. The nominal scale generally measures categories or classifications. For example, gender is measured on a nominal scale, and there are 2 values that the variable gender can take on: female and male. We can't perform arithmetic operations on these categories. 3 times female doesn't equal 2 times male. Even when the categories are numerical, we still can't perform arithmetic operations. Consider the congressional districts in the state of Oklahoma. District 1 plus District 2 doesn't equal District 3, nor is any order implied. District 1 is not necessarily bigger or more populous than District 2, same with District 3, and so on. And the same is true with the football jerseys. 80 divided by 2 doesn't equal 40 here, nor is a player wearing the jersey 80 better than one wearing 40, or vice versa. Even if the jersey numbers represent positions on the field, those positions are just categories. The ordinal scale measures categories that have an implied order or rank. A non-numeric example of an ordinal scale would be the medals awarded during the Olympics: gold, silver, and bronze. These are categories, but there is an order implied, as a gold medal signifies a better performance relative to silver, and likewise a bronze medal. A numerical example that's popular in the Midwest deals with tornado intensity ratings of EF1 to EF5. The intensity of an EF5 tornado is greater than that of a tornado rated EF1, but an EF5 tornado is not 5 times as intense. Similarly, the damage resulting from an EF2 and an EF3 tornado do not equate necessarily to one EF5 tornado. An order is implied, but arithmetic operations are not possible. A well-known numeric example that is regularly mishandled deals with questionnaires measured on what is called a Likert scale, the common 1 to 5 or 1 to 10 ordered scale ranging from strongly disagree with a given statement at hand to strongly agree. The distance between 1 and 2 is not necessarily the same as the distance between 2 and 3, nor is an answer of 4 meant to be twice the strength of an answer of 2. The interval scale measures numerical, not categorical data, where the distances between consecutive numbers have meaning. There aren't many examples of interval scale measures, but the most commonly discussed one is Fahrenheit temperature. With Fahrenheit temperature numbers, the temperatures can be ranked, and the amounts of heat between consecutive readings are the same. The distance between 51 degrees and 52 degrees is the same as the distance between 75 degrees and 76 degrees. Also, the 0 point is just a matter of convention in an interval scale, and not a natural or fixed 0 point. That is, a 0 measurement doesn't indicate an absence of value. In the Fahrenheit scale, 0 degrees Fahrenheit has no implied meaning, just another value on the scale. And it doesn't represent an absence of temperature, nor do positive and negative values have any particular meaning either. The ratio scale is the highest level of measurement, with the same properties as interval, but where ratios are meaningful. Also, the 0 point implies the absence of the value that we're interested in. Most anything we as engineers measure will be on a ratio scale: weight, height, length, volume, time, distance, and so on. Broadly speaking, variables fall into 2 categories: qualitative and quantitative. Qualitative data tend to describe characteristics that aren't measured with numbers and are measured with nominal or ordinal scales. Quantitative variables are those that are measured with numbers and are measured with an interval or ratio scale. Quantitative data are further described as being either discrete or continuous. Discrete variables are measured as integers and tend to represent counts. For example, the number of cantilever bridges in Oklahoma would be measured with an integer, as there can't be 8.34 cantilever bridges. Continuous variables are measured on a continuous number line. For example, the weight that a particular cantilever bridge can withstand can take on several decimal places and is thus a continuous variable. Let's take a look at a data set from the National Bridge Inventory from 2013, which contains information describing over 630,000 bridges on public roads in the United States. Shown is a subset of the more than 23,000 bridges that are found in Oklahoma. Let's distinguish the variables running across the top from the observations. Each row represents one bridge observation from the sample of bridges. We generally refer to the actual values of the variables for each observation as data. Here, the data are found in all the intersections of the columns and rows. Some of the variables include a bridge identification that I created, so it really has no meaning, the county where the bridge is located, the street or highway that the bridge carries, the object that the bridge is crossing, like a creek or highway, and its location. All of the variables I just mentioned are qualitative variables that describe each bridge in some way. The year that the bridge was built should likely be viewed as a quantitative variable, and likely as a continuous variable, as discrete variables are usually counts and years are not really counts. The span length is the distance between bridge supports, and the sum of the span lengths is the total length, both of which are quantitative and continuous variables. The sufficiency rating is a mathematical construct on a 0 to 100% scale that accounts for several factors describing the soundness of the bridge to stay in service. This scale would also represent a continuous quantitative variable. One last note about qualitative and quantitative aspects to data. The questions that we want to answer, those questions that spur data collection in the first place, tend to be qualitative questions. And answering them often requires us to collect quantitative data that in some way serves as a proxy to addressing that qualitative question. For example, perhaps we want to know whether one evacuation route is better than another. That's a qualitative question. Which one is better? To answer it, we have to determine what quantitative variable or variables might help us decide which one is better. Perhaps the quantitative variable we can use as a proxy could be average evacuation time per resident. We could simulate several evacuation scenarios for a large city, collecting the evacuation time for each of the simulated residents, then make a comparison. In another example, we might be interested in determining what material we should use to build a particular component part out of. We could build that component out of several materials, put them in place in our system, then observe different variables, including the deformation of the component under use, the weight the component adds to the system, and its time until failure, among others. With that collection of quantitative variables, we can draw a conclusion about the qualitative question broadly asked as, what material should we use? As engineers, we should always start with the root question we want to ask, then determine what variables we need to collect to best answer that question.